Okay, question two, we have a spring mass system that is given here with spring constant, some damper value, and some applicable forces. Simulation time 1 second, 300 frame per second. The assembly file is provided here. We're going to use that. On a stretch length is given 3 inch from the ceiling, from the top. An initial position of the mass is given as 1 inch from the top ceiling. So initially that would be compressed. So what is the equilibrium spring length? And then we have some applicable force that we are going to submit the graph. Okay, and then this is the one that we have to accurately report the given values. Okay, let's start. Drag this one here. I have opened the setup assembly here. Looking at the mate, one constant here, from here to here, and some distance, which is given here. So essentially the distance that I am seeing is 1 inch, which is consistent with what is given. However, for sake of simulation, we have to disable that. But I'm going to disable in the motion study instead of disable here in this assembly mode. So switch to motion study. We are going to change it to motion analysis. And then here, that was the mate that we are going to suppress. The other two mates is going to keep it in this area, and then from here we can keep it here. Essentially, by disabling this mate, the entire setup would have 1 degree of freedom, which would be the vibration along the vertical axis. Okay, so going for other, first we have to define gravity. I'm going to come here, define the gravity, and the value and direction is okay. So that's about that. And while I'm here, I'm going to change the simulation time to 1 second. I'm going to zoom in, and then as is given, it would be 300 frames per second. I just go by the order of the information given in the problem. After that, all we have to do, we have to define a spring here. Going to the spring section, it's a linear spring between this edge and another, which is here. A spring would be put up here. Information, K is 1. So you'll see here, K is 1 and C is 0.01. So K is 1, linear. And on a stretch length, we have to change it because it says is 3 inches. Okay, that's about it. So we have a damper, so we have to check damper. It's linear and it's 0.001, and the unit is consistent with the problem. And the rest of that, this information does not matter. This is as a matter of the graphic and the display of the spring here. So I'm putting here. Now the spring has been placed properly, hopefully. And then we are going to, the first one, find the equilibrium length. Essentially, we have to let it to simulate and see what is the, in what direction will it stay. So going to do that until 1 second was enough to this be. So if I simulate, it's going to go here and stay in the proper length. So in order to find what is the equilibrium spring length, you know that the spring length is something between here and here. So all I have to do, I have to graph the displacement between here and here. So what I'm gonna do, I'm gonna bring a graph, and it would be a linear displacement of and I'm going to select, let's say, magnitude between here and here. See if it's gonna work. Okay, so this graph shows the linear displacement between these two, and you will see that after some time, this is gonna stay in stay in some equilibrium length. So we are going to find what is this length that is being provided here. In order to find that, I'm going to, so this is called linear displacement. I'm going to export, and I call it, this is spring system. I'm going to call it mass or spring length, and then all I have to do is to open up that spring length, open up that CSV file that I have created. So this is the one. So it gives you all the frame per second, and then all we have to do, we have to come here and see what is the approximate value like at the end of that. So this would be like a 4.01 is the final answer approximately, or just for sake of argument, I can change to make sure that this is a number by 2 digits. Yeah, see that the final number is 4.01 inch. That is the final spring length. Okay, let me rename this to spring length. Call it here, and I am going to capture this one to a to proper save as. Going to bring it to here it would be okay, and then we have to apply some force. The question asks if we apply a force here, the P equal okay, that's a constant force, 2-pound force, then what is the equilibrium spring? Pretty much the same. And also it asks, before doing that, asks the vertical distance of the mass in both cases. So that was the graph that I was exported. Okay, so other thing, I'm going to close this. We have to apply a force. That is the force that is going to apply here. And that's a constant force. It was 2-pound force. Simulate that. It's going to stay. And then again, in this scenario, I have to show the plot that it stays at different value here. So first I'm gonna save it while I'm here. And that would be a screenshot that I'm gonna save to here, which would be Q2 plot 2. And then in order to find the spring lengths, we are going to do the same thing. Right click, export CSV, and here I'm going to export it to spring length with force. And then if I'm going and open that file that I have, spring length with force, open up in Excel, change this number to have 2 digits. So previous one, it would be 4 0.01, now it's 6.01, which makes sense because the force is going to pull out the mass and the spring more, and it is for 2" here, which makes sense. That is also consistent with the value of the K, because K is 2 pound-inch, meaning that if you have the force is 2 pound, therefore the spring would be a stretch for another additional 2", and then you have everything that you need. And one other thing that you may note, and that is the final thing, but also you will notice that this simulation requires a mass of this bar, which the mass is given by applying a material, which is a cast alloy steel here. Okay. Thank you. That is the end of this solution as well.